Okay, what's up everyone? Welcome back. Today we're entering section 6C. We're talking about orthogonal complements and minimization problems. Today we'll hit up orthogonal complements. Next time in part 2, we'll talk about minimization problems. They're closely related together, but to get to the minimization part, we got to do the orthogonal complement part first. So, let's talk about it. It's not too bad. In fact, a lot of the section has very easy proofs. So let's do the first bit. The idea is that if you take a subset U of a vector space V with an inner product on it, so an inner product space, I guess, then the orthogonal complement of U, which we'll denote by U with this upside down T, meaning U perp, think of it like saying right angle, right? Like two lines intersecting at a right angle. So U perp, the orthogonal complement of U, is the set of all vectors that are orthogonal to every vector in U. Easy way to write this, U perp is just the V's in V such that the inner product of U with V is equal to 0 for every U in U. All right, so nothing too crazy. Basically, if you want to think about this, it is the linear functionals on V that have U in their null space. So let me just kind of write that right there. So here, think of this. So since this guy is a linear functional on V, all we are doing is taking V and V such that U is contained in the null space of the corresponding element of the dual space that you obtain with the inner product. So that is, if you fix the V and you put whatever you want in the first argument, you've got a linear functional on V. And the question then is, what is its null space? If the null space contains U, then we're going to say that the corresponding V is in U perp. Okay, it's just the stuff that is orthogonal to everything in U. Not too bad. Think of it like this. If U is a plane in, say, R3, then U perp is just the line that is going through that plane at a right angle through the origin. So kind of a picture of it if you want. Here's R3, something I'm always terrible at drawing. And here's like some kind of a plane in it. Okay, there's some plane sitting here, whatever. Now if you, I'm doing a bad job of drawing this plane here. Let me draw this at a slightly better angle. So here, let me kind of go boop, 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 over to here. And then so I'm trying to say like, hey, look, like this thing is like intersecting the origin, basically, right? Like so. Yeah. Okay, then if we want to pick the orthogonal complement of this guy, draw this picture. Just think of the like the vector, the piece that goes through this. Maybe let me erase a little bit of that. I'm terrible at drawing these things, if you can't tell. So this is like, I'm trying to say it like goes underneath it, right? Just by putting some dashes on this chunk of the line. But basically it's the line through the origin at a right angle to that sheet. Does that make some sense? So if this guy here is U, then this guy here is U perp. Something like that. Okay. Well, let's talk about the properties of orthogonal complements. And the proof of this is pretty easy, though there's a lot of parts of it. So I'll just kind of sketch this out really quick. We'll go through it chunk by chunk. Here's the idea. So if U is a subset of V, then U perp is a subspace. Notice subset to subspace. If that reminds you of anything, then you're right. So think back maybe a little bit earlier to, I don't know, a discussion about, say, annihilators, something like that. Yeah, there is a direct connection here, exactly along the lines of what we talked about over here. So this says, take a subset, do the orthogonal complement, make U perp out of it, you get a subspace. So, part A. All right, now, if phi, or I won't even write this, I'll say this. I'll say if V is in U perp, then the inner product of U and V is equal to 0 for all U in U. So, U lambda V, which is equal to lambda bar, inner product of U with V, well, that's just lambda bar times 0, which is 0, for all U in U, and lambda V is in U perp as well. Okay, so we've shown that if V is in U perp, then lambda V is in U perp. Here, lambda is subscalar. I'll say that perhaps for any lambda in the field. I should have said that at the beginning, but it's fine to put it here. Okay, similarly, if, let's say, W is in U perp, then take U and V plus W now, and notice that this just turns into UV plus UW, which is just 0 plus 0, and that's 0. Okay, so V plus W in U perp as well. Clearly, U is 0 is 0, so 0, the 0 vector, is in U perp. Hence, U perp is a subspace of V. That is, we showed that it is closed under scaling, closed under addition, and has the 0 vector, so it's a subspace. All right, our next claim, part B and part C, are actually pretty straightforward. The first one says that the orthogonal complement of the 0 vector, the trivial subspace, is all of V, and that the orthogonal complement of all of V is the 0 vector. Let's show it. Part B. So, let's take the 0 vector, orthogonal complement. This is the set of V and V such that V0 is equal to 0. Yeah, right? Because there's only one thing in U here. But this is just everything. Right? Oh, okay. C. So I'll say by definiteness here. I won't even say by definiteness. By definition, I'll say. By the definition of the inner product. So this is one of our conditions. Okay, cool. Now for part C, if we take V perp, this is the collection of V's in V such that VW is equal to, or I'll even write this backwards. Oops, and I think I wrote this one backwards too, actually. I should have the 0 and the V in the opposite one. Notice it doesn't actually matter which one you do, just because if it's 0, then you can, conjugate and it's still 0. So nothing big lost right there, but I believe the way we defined it, we put the U piece in the first part. So I should be careful there. This is 0V instead of V0. Though it is the same set either way. We should be careful there. So this will be WV equals 0 for all W in V. Okay, so this is the collection of vectors V such that W inner product with V is equal to 0 for all W in V. notice this certainly contains the set of v's in V such that v is equal to 0, right? Since if the inner product of v with w is equal to 0 for all w in V, then one of those w's is v itself. What is the only vector? Actually, let me even be careful. I shouldn't say contained in. It's actually, I drew the containment the wrong direction. That is, this is a more stringent requirement. The vectors v that have an inner product with themselves of 0 certainly do not necessarily satisfy this just automatically. I mean, they do actually because of a kind of obvious consequence. But what I'm trying to say is that you have to have more things have an inner product of 0 here than you do over here. This is just one particular case of what's going on there. So if this is satisfied, then maybe this is satisfied, but you need to check it against all the other w's in V. So certainly this set is contained in that one. But this set right here, it's just all of the v's whose norm squared is 0. That means they have 0 norm. That's just the 0 vectors. So let me write this in there. V and V such that norm of V squared is equal to 0. But there's only one vector that has a norm of 0. It's the 0 vector. So V perp is 0. Oh, okay. Cool. Nice. A, B, and C down. Let's do D. D says that if U is a subspace of V, then U intersect U perp is contained in the set with 0 as its only member. Think about this one really quick. Well, when would you not actually get just the subset 0? Notice if U is a subspace, then both U and U perp do contain 0. So if U is a subspace, then the intersection of U with U perp is in fact equal to 0. But if U is just a subset, the 0 vector need not be in it. So then it may be the empty set if you take their intersection. All right, so here, let's just write this one out. D, U intersect U perp, this is equal to the set of, well, I'll write out what U perp is. I'll even write U intersect, then I'll write what U perp is. This is all the V's in V such that what? U V inner product is equal to 0 for all U in big U. But if you intersect this with U, well, then you're only looking at U's in U, or V's in U, in fact. So just writing that out, this is equal to the V's in U such that the inner product of U with V is equal to 0 for all U in U. And this is certainly, by the same logic as the previous line, contained in the subset with the slightly less stringent requirement that we have V in U such that V inner product is equal to 0, since one such V in U, or one such U in U, is V since V is in U. But this is just the 0 vector. That is the only thing with I should say contained in here, because we don't necessarily know that U is a subspace, so there may not actually be the 0 vector in there, but this is contained in the set. With only 0 in it, it could be empty if there is no 0 vector in U. But if there is, then that's the only thing that can be in here. Make some sense? Hope so. All right, these are just some long strings of equalities, and they look kind of messy, but it's not too bad in terms of the actual reasoning, I hope. So, if G and H are subsets of V, and G is contained in H, then H perp is contained in G perp. That is, the orthogonal complement of a superset is a subset. So it switches the order. This also may remind you of annihilators. So let's just write it out. If G is a subset of H, then think about this. Okay, H perp. Well, this is just the subset of all V's and V such that, all right, HV inner product is 0 for all h's in big H. Yeah? Okay. But now, since G is contained in H, having this hold, let me even write this sideways just for clarity. Having this hold certainly implies that it holds for all h's in G, right? That is a less stringent requirement. Okay, so this says that this is contained in the subset of V's in V, such that I will write GV equals 0 in inner product for all G in G. But this is just equal to G-perp. So H-perp is contained in G-perp. See? Nice. All right. We did all of them. Not too bad. Hopefully that's relatively clear. All we're doing is saying, hey, we're taking subsets where the inner product of the element with anything in the subset is 0. Just collecting all elements that satisfy that. All right, not too bad. The picture of it is exactly what you think. If you have a line in R2, then if you want to find its orthogonal complement, it is the line through the origin orthogonal to that line. Yeah? Cool. All right, so let's keep it going. Let's do some more. Okay, up next, we're going to prove a very important result about why we would care, that really explains why we would care about orthogonal complements in general. Namely, the reason is that they let us break apart vector spaces into direct sums of subspaces. So, here's the gist of what we're going to prove right here. We're going to say that if U is a finite dimensional subspace of V, which notice we're not assuming is finite dimensional itself, then V is equal to the direct sum of U with orthogonal complement. Okay. Let's let V be a vector in V, and suppose that E1 through En is an orthonormal basis of U. Okay, U is a finite dimensional subspace, so it has a basis. We can always take that basis and make an orthonormal one out of it using the Graham-Schmidt process, so it's got an orthonormal basis. All right. Then V is certainly equal to V plus 0. Would you agree with that? Yeah, I agree with that. But this is just V plus, well, let me write out what I'm going to say, V minus V. That's a fancy way of writing 0, yeah? Okay. And why I'm writing this is I'm going to say the following. V plus, and I'll write out what the ways I'm writing V. One way is as V inner product with E1. Or actually, I'm not even going to write it necessarily as, let me be more clear right here. I'm being a little bit too fast. So V plus 0, here's what I'm going to do. I'm going to write this as V plus, in particular, U, and then I'm going to write it as some W. Well, let me just write it, then I'll label everything. That sounded more confusing than it needs to. I'll write this really quick. So I'll take the inner product of V with E1 times E1 plus ... all the way down through the inner product of V with En, scaling En, and then I'll subtract the exact same thing off. Inner product of V with E1, scaling E1 plus ... all the way down through the inner product of V with En, scaling En. This will be much clearer in terms of what I'm trying to say now that I can actually point to things instead of just describing it. So thing minus the exact same thing. So this is V plus 0, yeah? Okay, now here's what I'm going to do. I am going to say that V minus this part be V minus inner product of V with E1 plus ... all the way down through V inner product with En, scaling En. So let's let this be W. Okay. And let's let U be the inner product of V with E1, scaling E1, plus dot, 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 all the way down through V inner product with En, scaling En, so that V equals U plus W. Do you agree with this? Since W here, this piece right there, this is just U. So W is equal to V minus U. So V minus U plus U is equal to V. Yeah? Okay. Well, now that we're here, notice the following. Certainly, U, little u, is in big U, since it is a linear combo of a basis for U. Okay. Moreover, watch this. Inner product of W with EK, well, this is just equal to the inner product of V minus U with EK, which is equal to the inner product of V with EK minus the inner product of U with EK. But let's just write out what U is. Well, I'll have this inner product of V with EK just sitting around, and I'll subtract off now. I'll just write what U is. So let me make these big angle brackets. I've got, and I'll write this in a different color now. This is VE1, E1, plus dot, 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 all the way down through inner product of V with En, En. And then I still just have my EK sitting there on the other side of the inner product. I just replace U with this. All right. And now all I have to do is split things up. So I've got my V and my EK. Okay. And now I'm just going to subtract things off, pulling out a bunch of scaling terms. So I've got my V, E1, inner product. Actually, even let me color code this to make the manipulation clear. So V, E1, inner product. Then I have an inner product of E1 with EK. And so I'll put this E1 back in the same color. Everyone see it? Plus dot, 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 all the way down through the end with a VEN inner product. And then there's going to be an EN, and then everything else will be in yellow here. Everyone follow along with how I'm breaking down this sum, splitting it up across the inner product by pulling out scalars and using the additivity of the inner product. Okay, cool. Now, all I have to do is notice that everything here is going to go away except for one of them, since this is an orthonormal basis. So what I'll end up getting is I'll get back VEK, and then there's going to be an EK right here, and in the other color, switching now, I'll get an EK as well. Everything else is zeros. But hey, inner product of EK with EK, that's the norm of EK squared. If it's an orthonormal basis, that is 1 squared. So I just get VEK, inner product, minus the inner product of V with EK, which is a fancy way of saying 0. So W is in U perp. Since W is orthogonal to every element in a basis of U. Hence, V is certainly equal to U plus U perp. That is, I just told you exactly how to write V as something that lives in U and something that lives in U perp. It is this U plus W business right here. Okay. Moreover, this sum is direct since U intersect U perp is equal to the 0 vector by the previous theorem. So we're done. That is, we just wanted to show that v is equal to the direct sum of u with u perp. And we got that. Not too terrible. Okay, here's a nice consequence of this. If v is finite dimensional and u is a subspace of v, then we can use the fundamental theorem of linear maps, or really, in a certain sense, to say the following, that the dimension of u perp is equal to the dimension of v minus the dimension of u. That is a pretty smooth little fact right there, isn't it? Yeah? Okay, kind of cool, yeah? So, neat. All right, let's keep going. Let's do a little bit more and find out what else we can say. Well, actually, wait, before we do, let me say a tiny bit more about this, since I realized I may have been a little bit pithy. You can use the fundamental theorem of linear maps to get this. You can also just get it slightly faster by looking at this right here and noticing that the dimension is additive across direct sums. So, since the dimension of v would then be equal to the dimension of u direct sum with u perp, that is equal to the dimension of u plus the dimension of u perp. So, just do a little bit of arithmetic and you get this fact right here. So, hopefully that's, I guess, relatively more clear than saying, than some appeal to the fundamental theorem of linear maps. All the same, let's keep it going. Let's go on to the next little bit right here. All right, next up, we're going to show that the orthogonal complement has a very nice property. That is that if you do it twice, you get back what you started with. And notice this will only be true for finite dimensional subspaces U of a vector space V, which need itself not be finite dimensional. So some screwy things can happen in the case of infinite dimensional spaces, but let's restrict ourselves to the claim that we're dealing with a finite dimensional subspace of V. So notice that U perp, just by definition, is equal to the set of all v's in V such that the inner product of U with V is equal to 0 for all U in U. So U perp perp, the orthogonal complement of the orthogonal complement, this is equal to the v's in V such that I will say WV is equal to 0, and the inner product there, for all W in U perp. But notice that if U is in U, then WU, well, this is equal to U comma W orthogonal complement, which is equal to the orthogonal complement of 0, which is just, or sorry, not orthogonal complement, the conjugate of 0, which is just 0, whenever W is in U perp, right? That is, U perp is just all of the vectors such that U inner product with that vector is equal to 0 for any U in U. So if you grab some U and you bounce it off such a W, well then just conjugate to flip things around and use the part from the first bit to say that you get 0. And the conjugate of 0 is 0. So U is certainly contained in U perp perp. That is, we've shown that all of the U's in U's are elements V that satisfy this condition right there. Nice. Okay, okay. For the reverse inclusion, suppose that W is in U perp perp. Now maybe I should say V instead of W. How about, since I've written things with a W for elements of U perp in that second thing up here. So let me say a V. Let's suppose that V is in U perp perp. Okay. by the previous result, v is equal to some u plus some w, where u is in u, and v is in u perp. Do you agree with this? Or w is in u perp. Sorry, I'm writing too fast. W is in u perp. Yeah? So far? Feeling all right? Okay. Cool, cool. So, now just thinking about this, we've got v is u plus w. So v minus w is equal to u, which is in, now, let me make sure I've said this right. So you've got, or no, I want to say this the other way. Yeah, I'm sorry, I'm being silly here. So here, I've got my letters backwards from what I wrote in my lecture notes here. So I'm trying to make sure I flip them correctly on the fly, and I don't want to mess it up because U's, W's, and V's all look very similar. So here's the idea. What we want to do is we want to take something in the double dual and show that it lives in U. Yeah? So the idea of it is to take this stuff. We're going to find the perp of the perp and show that it lives in both U perp and the intersection of U, or the intersection of U perp with U perp perp. Then we'll get that something is 0 and will be set. So we're going to show in particular that W is equal to 0. Yeah? So V minus U here is equal to W, and W is in U perp. Okay, so V minus U is in U perp. All right, but think about this. V is in U perp perp. So since we've got W in U perp and V minus U in U perp, and since U is contained in U perp perp, V minus U is in U perp perp, right? Hence, V minus U is in the intersection of U perp, so since it's in U perp, and also in the perp of U perp. I know we're saying the word perp a lot, seems sort of silly, but we know that this is 0. So V minus U is in U perp intersect U perp perp, which is just the 0 vector. Hence, V minus U equals 0, and V is in fact equal to U, which is, notice now, from what we did, in U. So we started with something in U perp perp, and we showed that it's in U. So U perp perp is contained in U, since everything in it is also in U. All right, now we've shown that U is contained in U perp perp, and we've shown that U perp perp is contained in U. Therefore, U is equal to U perp perp. Kind of nice. That is, if you do this perp thing twice, you get back what you started with. Sort of like multiplying by a -1, yeah? All right, pretty cool, pretty cool. This gives us some nice little consequences. It says the following. So if U perp is equal to just the 0 vector, this happens if and only if U is equal to V for U a finite dimensional subspace of V. Okay, so not too bad. If we just go back up to what we just did, it says you perp it twice, you get back yourself. Yeah? So I'll take a perp of this thing and a perp on the other side. Yeah? Okay. But we know that this says that u is equal to v, since u perp is equal to u, and the orthogonal complement of just the 0 vector is equal to v. Oh, okay. So that's the proof of it. Not too bad. Pretty straightforward. So all we had to do is use the fact that you apply it twice, and you get back the same thing you started with, and then use the fact that the only thing that's orthogonal to everything in V is the 0 vector. Okay, let's keep it going. Let's do some more. Okay, so up next, we're going to talk about the orthogonal projection, which is something that we've already used. Here's the idea of it. If you've got U, a finite dimensional subspace of a vector space V, particularly one with an inner product space, which need not itself be finite dimensional, we're going to say that the orthogonal projection of V onto U, it's the operator Pu in LV, so it's a linear operator on V that takes V, and if we write it as a direct sum of a piece that lives in U and a piece that lives in U perp, gives you back the piece that lives in U. So, since you can write every vector V as something in U plus something in U perp, you can just map any vector V to the piece that lives in U. Nice. Since the sum U plus U perp equals V is a direct sum, this is a unique U in U and a unique W in U perp. So this mapping is well defined, and it's not bad at all. We got a projection. In fact, we've seen this guy already in a previous theorem. Actually, wrong page. Here we go. Right here. So this business right here, this little u here, when we said, hey, let's write V as a piece that lives in U, that is, it's the inner product of V with E1, scaling E1, plus all the way down to the inner product of V with En, scaling En. This is, here, going back, this here is Pu of V. Oh, okay. So this is just the orthogonal projection of V onto U. Basically, just pretend that V lived in U and you were writing it as a linear combination of the basis elements. You would just use this formula right here. We did that last time. We showed that, hey, if you've got a vector V in a finite dimensional inner product space and you've got an orthonormal basis, then the coefficients in the linear combination of those basis elements that allow you to write that vector as a linear combination of the basis elements, the coefficients are just the inner product of the vector with the corresponding basis element. So this is basically just saying pretend that V lived in U and write it as a linear combination of an orthonormal basis. It may be the case that V does not actually live in U, but this little chunk that you get does live in U, and bada boom, we've defined this nice linear map. So going back to the new stuff, now, here is the gist of all of it. We're going to have this map right here, and we can actually write out what it is for an orthonormal basis E1 through En of U. Pu of V is just Pu V is equal to VE1 inner product scaling E1 plus dot 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 all the way down through VEN scaling En. Not bad at all. Okay, so just a little note right there. Let's prove a bunch of properties here, or at least kind of sketch out the proof of it. Nothing here is too terrible, though this is such a long series of things that it may benefit us to not spend a terrific amount of time writing out the in-depth proof of every one of these. I will skip over a few of them. So let's go through it. Let's see what we can do. Our first thing says that Pu is a linear operator on V. This is easy. It's just procedural. Nothing too bad there. The next piece says that pu of u is equal to u for every u and u. This follows directly from this fact up here. That is, from this formula I gave you right there, that's just immediate. That is, if u is in u, then this will just give you that. Also, an easier way to see it is the fact that if you write u as something in u plus something in u perp, well, u intersect u perp is the 0 vector. So if you want to write it as a sum of something in u and a something in u perp, then the thing in u is going to be u itself, and the thing in u perp is going to be 0. So pu of u is u. Okay. Pu of w is 0. All right. Not too bad. So this is just straight from the definition of pu. This is directly from this or from the definition of pu, the previous one. The range of pu is equal to u. I also claim that that's pretty straightforward. After all, if you take v as u plus w for u in u and w in u perp, and you send v to u, then you certainly will be able to hit all of the u's in u. That is, if we use part B, it says that pu of u is equal to u, so certainly you hit every single u in u. Okay. And if we use C, we can get this with the fact that v is equal to u, direct sum with u perp, to say, hey, look, the piece in u gets mapped to u, the piece in u perp gets mapped to 0, and the fact that the piece in u perp gets mapped to 0 just lets you do part E as well. Same logic. All right. Not too bad at all for the next one. F says that v minus pu of v is in u perp. So v equals u plus w, u in u, w in u perp. Okay. But look, u is equal to pu of v plus w. So this says that v minus pu of v is equal to w, which is in u perp. So this here is the logic for that one. Nothing crazy. Okay. So look at this. If v is equal to u plus w, which it always is since v is a direct sum of u and u perp, then pu of v is equal to u, and pu squared v, so just do it twice, is equal to pu of u, which is u. Oh, okay. Look, you get the same thing out from squaring it for any vector v and v as if you just do it one time. Nice. All right, and then finally, not quite finally, close to finally, the norm of pu v is less than or equal to the norm of v. So the norm of pu of v, well, this is just equal to the norm of v minus w. Okay, which is certainly going to be less than or equal to the norm of v. Do you agree with this? Well, if you don't, we can write this in a slightly different way. So this is just u. If you want to see this in another way, I can just say this. Actually, this is probably easier. Norm of u is less than or equal to the norm of u plus w, which is equal to the norm of v. Oh, okay. Since u and w are orthogonal. Maybe that one actually deserves a little bit more. So for part H, here's the idea. Since v is equal to a direct sum of u and u perp, all we have to do is write v and v as v equals u plus w, where u is in u and w is in u perp. Okay. Since pu of v is defined to be equal to this little u right here, and since u and w are orthogonal, we get the following. So here's what I'll write. I'll write the norm of PUV. Well, that's just equal to the norm of u. And I'll say that the norm of u is certainly less than or equal to the norm of u plus the norm of w, which I claim is certainly, if we square everything, going to satisfy the following. So, square it all. This is in fact equal to the norm of u plus w squared via the Pythagorean theorem. So notice, all I'm saying is that the norm of pu of v squared is equal to the norm of u squared, and that's certainly less than or equal to the norm of u squared plus something that is not negative. Okay, so since this is u squared plus norm u squared plus norm w squared, and u and w are orthogonal, well, that is equal to the square of the norm of u plus w via the Pythagorean theorem. Taking a square root, PUV in norm is less than or equal to the norm of u plus w, which is equal to the norm of v. Okay, so we got h. Now, finally, I, the piece that we actually, I guess, referenced earlier, so this idea that pu of v is just these, this linear combination of an orthonormal basis of u. Let's prove that. So if E1 through EM is an orthonormal basis of u and v is in v, then pu of v is equal to this big old linear combination of E1 through EM. Okay, so all you have to do here is just do it directly. So if u is in u, then u is equal to u E1 inner product scaling E1 plus dot 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 all the way down through u En m, I guess, scaling em for any ONB orthonormal basis E1 through EM of u by a previous result. That is, we proved this last time in section 6b. Okay, so since pu of v, which is equal to pu of u plus w, is equal to u, this just says that u we get that PUV is equal to all of this. U E1 plus dot 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 all the way down through U EM. Okay. But notice, since W is in U perp, the inner product of any U with W is going to be 0. So this thing over here, which is just pu of v, as we've described it, is in fact just going to be equal to, I'll write it vertically, I guess, just for clarity. I'll write it still as u e1. I'll put this in parentheses plus 0 e1 plus dot 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 all the way down through u em inner product plus 0, all in parentheses em. And all I have to do is rewrite out what all of these things are. I'll have my w e1. That's equal to 0, as we just said. And go all the way down, and I get inner product of u with em plus inner product of w with em, which remember is just how I'm writing 0 right there. And then I have my em. And now all I have to do is combine. Oh, okay. So this is the inner product of v with e1. Since I can just add those together and get u plus w, e1 plus dot 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 all the way down through v with em. And now we were done. We've got what we want. So that's not too bad either. All right, that's a little bit of a messy, long one right there, but hopefully we went through it to a satisfactory degree of detail. Some of the early ones are not too bad. They're relatively straightforward, and hopefully I've given you enough detail to finish the proofs yourself if you want to see them in a more formal way. But let's go on just a little bit farther and revisit the Riesz representation theorem to close out today. Okay, we'll make this last note brief. Basically, we want to just look at the Riesz representation theorem in a way that is similar to what I described at the beginning. So, here's our claim. If V is finite dimensional, then for each V in V, let's define phi V in the dual space by phi V of U is equal to U inner product with V for every U in V. Okay, so this just says, hey, take a V, you can fix that in the second argument of the inner product, and then, now, you've got a linear functional. Our claim is that the map that sends V to phi V is 1-to-1 and onto. That is, it is a bijection. So, in the case where V is finite dimensional, V and its dual space are isomorphic. And one isomorphism, if V has a we already knew that. We already knew that the dual space of V, if V is finite dimensional, is isomorphic to V itself, and you can take any basis and turn it into a dual basis to see that. But what this is saying is that one way, if V has an inner product on it, to recognize this isomorphism is to use the inner product. Kind of cool. Okay, so let's just go through it in one case. Let me make a quick note. So, if f is equal to r, then phi of lambda v u is equal to the inner product of u with lambda v, which is just equal to lambda bar, inner product of u with v. But if f is equal to r, this is just lambda u inner product v, which is lambda phi, before I try my lambda phi v of u. So, I'll say in the real case, the map T of V equals phi V is linear, i.e. T is a linear map from V to the dual space if V is a real inner product space. But if the field is the complexes, then T is not linear, which is unfortunate. So let's just sketch the proof in the case that T is a linear map. So if f is equal to r. So let T be the linear map from V to V prime, be T of V is equal to phi of V. Then notice that null T, well, this is just the set of V's in V such that T of V is equal to 0 in V prime, but that's just the set of V's in V such that U V is equal to 0 for all U in V. Yeah? Since the 0 map in V prime is just the map that sends every single vector to 0. Okay. But hey, would you look at this? This is certainly contained within the set of V's in V such that V inner product with itself is equal to 0. But that is just the set 0. Oh. If it has to hold for all u's, then it certainly has to hold for the particular u that is also equal to V. Yeah? Okay, so this is just, hence, the null space is trivial, and T is injective. Since dim V is equal to dim V prime, T is then also surjective and an isomorphism. Wow, not too bad at all. Okay, so this is a good sketch of the proof if the field is real. Now, if f is the complex numbers, this doesn't work, since we can't use this nice fact about linear maps between spaces of the same dimension that says that having a trivial null space gives you surjectivity and invertibility. So if f is equal to c, in this case, the above works to show that the set of vectors v in V such that phi v is equal to 0 is just this. That is, well, we can't say null T now because T is no longer a linear map. Just the map that sends V to phi v has certainly a set of vectors V such that phi of V is equal to 0. Well, for exactly the same reason we outline right over here, this is enough to get injectivity. So the above, by the above I mean this business right there, that works to show that the set of vectors V and V such that phi of V is 0 is just 0. For surjectivity, all we need to do is note that phi of the 0 vector is the 0 functional, and for V in V, V not equal to 0, the null space of phi V has dimension, think about this, n minus 1. So null phi V perp is 1 dimensional. Yeah? Okay. The same is true of any phi in V prime. certainly, right? So all we need to do is match up, I'll put that in parentheses, the null spaces orthogonal complements and scale appropriately. This is not too terrible of a process. Basically, all we're saying is, hey, look, something in the dual space sends a vector space of, I won't even say n minus 1 right here since that may be confusing. I'll say dim v minus 1. How about? Look, here's all I'm saying. All I'm saying is that a linear functional sends v, a space of dimension v, to a space of dimension 1. So, by the fundamental theorem of linear maps, its null space has dimension dim v minus 1. So, all you got to do is take the orthogonal complement of that, and you get back a one-dimensional subspace. Okay. Same thing is true of any old linear functional. It's true for anyone, no matter what. So it's certainly true for these phi v's. All right. All you have to do is just make sure that these null spaces have the same orthogonal complement. Okay. You pick a v to make the null space have the right orthogonal complement. Not too bad. And then from there, all you got to do is just scale. So anything that has the appropriate null space, you can just scale it into another thing with that same null space. Cool. All right. For details, see page, I believe, 216 and 217 in the book. I won't spell it out here since we're already running pretty long. So let's just leave it there. Next time we'll talk about minimization problems. It's not too terrible. It will come along from the orthogonal projection in a nice way. Basically, the gist of it is that, hey, if you've got two lines and you want to understand what the, you got two different lines and you want to understand what the closest point on one line is to another, all you have to do is drop down at a right angle. Yeah. So if this is v, then the closest point on this other line to v is the one that is right below it, such that this line down there has a right angle. So that's the gist of it. It won't be too bad. We'll prove this next time. All this stuff, we'll talk about how orthogonal complements let you solve minimization problems, and it'll be fun. We'll do a good example, and you'll see that this actually has incredible usefulness when dealing with applied mathematics, because you can provide extremely accurate approximations, and it did not seem like we were doing something that had any applications probably at this point, since everything has been pretty theoretical so far. But I'll show you next time that we actually have been building up something that lets us do really useful stuff in the real world. So I'll see you then. Have a good one.